Welcome back to part 2 of the review podcast on transformations of functions, and now we're going to look at dilations. So the function, again, we have our same old function f of x that we've been looking at in the previous parts, but now we're going to look at the function g of x, which is 2 times f of x. And this is our function diagram. If this is f of x, this is 2 times f of x. I take the output of f and I multiply it by 2. And the function g is the act of doing the function f and then multiplying the answer by 2. Just like I did with translations, that means that I'm going to take the output f of x to get g of x. I'm going to multiply it by 2. Negative 12, 4, 4, 12. If I plot these points and connect the dots, I can see that I have a similar shape to what I had before, but it looks like it's been stretched. One of the things that people get a little bit thrown off about when we're talking about vertical dilations is that they get confused about where the dilation is centered around. I don't know if that makes any sense. For instance, right, if you look at the green graph compared to the blue graph, people might look at that and think, oh, it's stretched vertically, but it's also been moved up. That's not the case here, right? Because all of these vertical dilations are centered along the x-axis here. In other words, right, if I look at these actual coordinates, right, this point is twice as far down, this point is twice as far up, this point is twice as far up, this point is twice as far up. I haven't also shifted it upwards. It's just that more of the graph was above the x-axis to begin with. So when I double all of the output y values, it makes it seem like the graph is even more top heavy. So one thing you want to think about when you're going from the graph, right, if I give you f of x and g of x and I ask you to figure out what's going on, actually look at the coordinate values. Don't just kind of eyeball it by looking at the picture to see what's going on. Okay. So that's g of x. I think that should make a lot of sense. And to summarize, right, if g of x is some constant c times f of x, the function g of x is a vertical dilation of f of x by a factor of c. I want to take a second and just talk about vocabulary. We talk about dilations by a factor of c because dilations are multiplying, and factor is the word that we use to talk about a number that you multiply. It doesn't make any sense to talk about translating by a factor of some number. Okay? So if g of x is 19 f of x, then all the y values are 19 times as large, and g of x has been stretched 19 times taller. If h of x is 1/4 f of x, then all the y values are 1/4 as large, and h of x has been shrunk to 1/4 as tall. Okay? So that should be pretty intuitive and familiar to you from your previous understanding of transformation of functions. Let's go ahead and look at when the multiplicative factor is in the argument instead of in the function value. Okay. So here we have the function that we're going to look at is going to be h of x is f of 2x. So just like we had before, right, we're going to take x, we're going to multiply it by 2, we're going to take it and we're going to put it into the function f, and then some y is going to come out. Now h is the multiplying by 2 and the f together, but what is going to be more useful for us to think about what's going on in the graph is to think about the new input to f of x is going to be x in h of x, then times 2, right? This 2x number is the input to f of x. So again, if this is an accurate table relating x and f of x, right? But if I wanted to make a table relating x and h of x, what I could do is, just to be lazy, right? I could say, hey, I don't want f of x anymore. I want h of x. Oops. Whoa. Okay, if I didn't want to make a table for f of x anymore, I wanted to make a table for h of x, I could start with f of x, right, the relationship between the input and the output of f of x, but the input to f isn't going to be h anymore, right, or sorry, x anymore, it's going to be x times 2. So let's think about this number that's the input to f, right, these numbers here, which were the input to f previously. Let's say that this is now 2x. Right? 2x is what went into f. So if I think about -8 going into f, right, that number is 2x now. So if that's 2x, what does x have to be? Well, half of that, right? -4, -2, 3, and oops, that's a lie. Not 10, but 5, right? Okay, so if I go ahead and I plot those points, And again, note that I'm plotting this as the input x and h of x is the output, right? So I'm plotting the new function h of x, and then I connect the dot. We can see that this new function isn't twice as wide, it's half as wide, right? And again, this is pretty counterintuitive. People desperately want f of 2x to be twice as wide as f of x is, but it's not true. And again, if we think about the domain, that can help us see why, just like it did before. Okay, so let's think about the domain. Again, if I think about the domain to f of x, right? For f of x, right, the x values had to be between -8 and 10. Oops. Now, h of x, which is f of x plus 4, or no, sorry, x times 2, 2x. Oh. F of 2x. Then 2x is what needs to be between -8 and 10. And if I solve that, right, I need to divide everything by 2, which is telling me that -4 and 5 are the bounds on x, not -8 and 10. It got narrower, it didn't get wider, because 2x is what needed to be between -8 and 10, not x. I need to have room to double x before it gets put into the function f. So this, again, while counterintuitive, this should be kind of familiar to you because this is not the first time you've heard about a horizontal translation. So to summarize that, if g of x is f times c of x, the function g of x is a horizontal dilation of f of x by a factor of 1 over c, not of c. So some examples, if g of x is f of 19x, then it has all x values 1/19 times as large as f of x. G of x has been shrunk 1/19 times as wide. That's a typo. So 1/19 times as wide. There we go. F of 1/4 x has all x values 4 times as large as an f of x, right? Because 1 over 1/4 is equal to 4. Sorry about the pen there. H of x has been stretched to 4 times as wide, right? So again, this is counterintuitive. One of the ways that I like to think about it, kind of putting together the translations and the dilations, that when I am modifying the argument, right, when I am modifying the input to a function, either by a dilation or a translation, it kind of does the opposite of what you think it's going to do. If I have f of x plus 4, that's going to move it to the left and not the right. If I have f of 2 times x, then it's going to multiply it by 1/2 and not by 2. Those are for inside transformations, which is another way of talking about transformations that are acting on the inside of the parentheses in the argument, as opposed to outside transformations, which act on the function value. Okay, we're motoring through this. Let's quickly talk about reflections, which are quite easy when you already know about, excuse me, dilations. So, one way of thinking about a reflection is that it's just a dilation by a factor of -1, right? So if this is my my function machine, right? If I think of g of x as negative f of x, I'm going to multiply by -1, right? My function g is the act of doing the function and then taking the output, multiplying it by -1. If I actually take the outputs and I multiply them by -1, we can see what happens to the function. Let's go ahead and plot these points. When we connect the dots, we can see that we have the same thing that we did originally, only flipped vertically, right? So the y values have changed. It's been flipped over the x-axis. Sometimes people get confused about that, right? When I'm changing the x values, it's a reflection over the y-axis. When I'm changing the y values, it's a reflection over the x-axis. But this is a vertical reflection, or a reflection over the x-axis when I have negative f of x. Let's quickly take a look at the last case, which is going to be f of -x. So if h of x is f of -x, I'm going to take the input and multiply it by -1 before it goes into f. Again, right, the new input to f of x is going to be x times -1. So if I want to modify this table and have it be for h of x instead of for f of x, right, what I want here is this is going to be -x instead of x. So what does x have to be? Well, +8, +4, -6, -10. If I go ahead and plot those points and connect the dot, I can see that I had the same graph that I had before, except for flipped horizontally, this time over the y-axis. If I want to summarize that, right, if g of x equals f of negative x, the function g of x is a horizontal reflection of f of x over the y-axis. Okay, so that is a very brief review of transformations of functions. Hopefully this is all familiar to you. We're going to be looking soon at applying these transformation of function principles to new types of functions that we're going to be learning about shortly.